So today is actually, excluding today, we only have one lecture left. So what I want to finish is obviously this chapter, the network flow. Okay? And then hopefully we're going to start most likely the last chapter, which is empty completeness. Okay? So we finish this discussion of that Ferguson and the tandem cars. Okay. And then, the next one is the minimum cut. So what is minimum cut? Okay, when you designate the network flow to a graph, okay, so you want to cut the edges. Okay. So given a graph G, okay, that consists of like B and E, okay, the cut will break the vertices into two subsets. Okay. One is A, one is B. Okay. And A, B are has these two subsets have the following properties. First, the set A, and the set B, they are disjoint. And the union of A and B is B. Okay, so this is what we call a partition. Okay. And to be more like specific, okay. Remember we have two spatial nodes, right? The source S and the sink T, right? So the source S belongs to the subset A, and the sink T belongs to the subset B. Okay? So once you partition the nodes into two subsets, okay, you can observe the flow coming in and getting out of these two sets. Okay, you will find something very interesting. Okay, so obviously, if source is contained in A and the sink T is contained in B, obviously, okay, because the flow goes from source to sink, you would imagine, there will be more flow coming from the subset A to the nodes in subset B. Okay, this is a very simple intuition, and it is true. It is true. Actually, okay, we can say something more interesting here. Okay, it's like this. Okay, the current maximum flow, okay, can be observed by, accounting the incoming and outgoing flow in this card. So for example, okay, if you look at this figure, this is the flow network, obviously. Okay, so my first question for you, okay, what is the maximum flow here? What is the maximum flow here? Can somebody answer me? Oh, by the way, for each age, there are two numbers. Okay, the first number indicates the current flow assignment. The second number indicates the capacity of this age. For example, okay, from S to 1, there's like a 12/16, meaning the capacity for this link, okay, for this age is 16, and the 12 have been used. Okay, 12 have been used. Okay, so can someone tell me, do we have additional augmentation path exist here? You could try to do either Edmund Kahn or Ford Robinson. Okay, so you will see that, well, from S you go to 1, one goes to 2, but obviously you cannot go from 1 to 2 because the capacity is 0. Okay, so if you you can go from 1 to 2. Okay, because you have 10 capacity left, and which is not used. Okay, and then you cannot go from 1 to 3 because all the capacity have been used. So once you go to 2, okay, well, the only, you can also go back to 1, but it's probably not going to help. Okay, so you go from 2 to 4. Okay, because there's still like some capacity left. Okay, for the age between 2 and 4, and then from 4, you will find that all the outgoing ages, the capacity is gone. Okay, so you got that here. Okay, so if you go from S to 2 directly, you face the same problem. So basically, you are not able to find additional augmentation path here. Okay, so in other words, we already reached the maximum flow. Okay, so what is the maximum flow? 23, right? 23. Because obviously, if you look at the key, okay, it received 19 from the top edge. You receive 4 from the bottom edge. So total amount will be 23, right? So, okay, now let's just arbitrarily cut this graph. So we cut this graph by this dotted line. Okay, so all the nodes belong to the left side. Okay, for like the set A will be S1, 2, and 4, and nodes belong to set B will be 3 and the T, right? So if you look at the edge in between these two sets, if you look at the edge in between these two sets, okay, you will find that here there's a 12, okay, unit of flow going from 1 to 3. Okay, so we have 12 here, and we have We don't use any, we don't have any flow in here. And then we will have like 7 to go from 4, which is also like one node in set A to 3. Okay, with 7. So 12, 7. And then we have another 4 that goes from 4 to T. So totally we have 12 plus 7 plus 4, 23. Is this, a random, result? The answer is no. Okay, you can randomly cut it. Okay, for example, let's cut it here. Here. Again, it breaks the nodes into set A and set B. And you can see that we have 3 edges in between these 2 sets, right? So you can see we have 12 here, 0 here, and then 11 here. So 12 plus 11, again, 23. Okay? So you may say, that means you have to cut this, the set A and the set B, they have to be continuous. The answer is again, no. Okay? Let's just pick, well, let's assume node 1 and the node 4 and the T, okay, are in set B, and then the rest of the nodes are in set A. Show it. Okay? So node 1, 4, and T, obviously 1, 4, and T, they are not connected, right? They're not connected. Okay? And the rest of the nodes will be S2 and 3, right? So let's have a look. 1 here. Okay, how many? We have like 12 incoming. And then nothing go out, nothing comes in here. And then we have 12 outgoing, so it's 0 here. And the 4 and the T, okay, how many? We have like 11 here. We have 7 here. So with incoming 11, and 7 is gone. So 11 minus 7. And then minus 7 and plus 19. So 11 minus 7, we get 4. 4 plus 19, again, 23. Right? So regardless, it doesn't, we don't have to have nodes in step A or step B to be connected. No. Like, the edges, if you count like the flow between set A and set B and you add them up, it will be the maximum flow. Actually, it will be the total flow your node T receives. Okay, the node T receives. I mean, because we may still have augmentation path, right? Now, for this particular example, we don't have additional augmentation path. Okay, so we already reached the maximum flow. But the thing that I just discussed, we random cut into 2 sets, and the total flow from set A to set B, okay, will be the flow received at node T. This is true, okay. Even when T is not receiving the maximum flow. Okay, so this is what we call cut, a graph cut. So, how do you do it? this is actually easier than you may think. Okay, think about this. We start from, again, we are doing induction. So what is the base case? Remember, this cut require one set to contain node S, one set to contain node T, right? Okay, so it may be easier if we just consider like, let's say node, set B contain only one node, node T, and all the rest of the nodes belong to set A. All the rest of nodes belong to set A. Okay, so in this case, obviously, the flow, okay, the total flow from set A to set B, because B only contains one node, which is node T, right, is the flow currently received at the sink, right, according to the definition of like, whatever you receive at the sink, that's the current flow like you are getting from this flow network, right? So this is obviously the case, right? According to the definition. So if I use this graph as example, then I'm looking at here. Okay. Oh, from all the nodes in A to this only node in set B, well, it will be only these two edges, and the sum of these two edges will be 3, and which will be the capacity will be the flow received by the sink node T. This is obvious, right? So now let's consider adding nodes to this set B, because set B is only one node. It's only one node, so we could increase the nodes in set B. So say this is like this is A, this is B. Say, the links between A and B, the capacity the total flow equal to the flow received at the sink. Say this is like an induction hypothesis. This is true, okay? But now we need to grow set B by one additional node, right? We need to grow one node, into set B. So now, let's randomly pick a node in set A. This B is T. We have the source node S. We couldn't pick source node S. Okay, we wouldn't pick source node S. Okay, but any other node. We could pick any other node. From A to B. So we move this into B. So B becomes like something like this. So originally said this node has like some link to B. Now that link will not be considered. Will not be considered. Okay? So there's a property. I mean, you guys may still remember. I hope you guys still remember. It's like in the flow network. In a flow network. Okay. After you assign a flow, I'm not saying like at the end. Okay, I'm saying like anytime during the process of finding augmentation path. Okay, for any node, the incoming flow and outgoing flow. I mean, like if it's not the source, it's not the sink. Okay, any other nodes, the incoming flow and outgoing flow have to be the same, right? The incoming flow and outgoing flow have to be the same. If not, if incoming flow is more than the outgoing flow, the water will build up, right? The water build up, I mean, at that node. So we will have issue, right? If the incoming flow is lower than the outgoing flow, I mean, that node has to produce some water, otherwise it's not sustainable, right? Yeah, we talked about this long time ago, right? So let's think about it, please. Okay, yeah. Once you include this node into set B, I mean, obviously there's some like incoming edges to this node, and there are some outgoing edges from this node to other nodes. I mean, some of the outgoing edge may go to B, some of the outgoing edge may go to A. I mean, by the way, as I said, the incoming edge, the flow in incoming edge plus the flow in outgoing edge, I mean, minus the flow in outgoing edge, should balance each other, right? Should balance each other. It will balance each other, right? So, I mean, like some edge, is in between. Let's call this node like P. Okay, some edge from P may go from P to the some nodes in P instead. Some outgoing edge may go from P to some nodes in A, the set A. Okay, but regardless, all these like incoming flow and this outgoing flow should balance each other. So what does that mean? That means, okay. So say the P, the flow from P to A to B. Okay, flow from P to B. Okay, that's part of outgoing flow, right? Plus the flow from P to A. Okay, it will be the same as flow from A to P, right? Actually, you may also have some flow from B to P. Okay, so these two add up